In this lesson, we will learn how to solve equations involving square roots. We will begin with a relatively simple example. As you can see here, the variable x is inside the square root. To pull the x outside the square root, we'll raise both sides of the equation to the power of 2. We do this because of the property that says, if we raise the square root of some value k to the power of 2, this will be equal to k. So on the left-hand side, the square root of x all to the power of 2 will be equal to x. On the right-hand side, we have 5 to the power of 2, which is 25. So the solution here is x equals 25. Okay, here's another equation. To solve this one, we'll first raise both sides to the power of 2. On the left-hand side, the square root of x minus 2 all to the power of 2 is equal to x minus 2. On the right-hand side, 3 to the power of 2 equals 9. From here, we can add 2 to both sides to see that x is equal to 11. Okay, how about this one? To solve this one, we will once again raise both sides to the power of 2. On the left-hand side, we get 3x minus 5, and on the right-hand side, we get x plus 10. From here, we'll subtract x from both sides, and then add 5 to both sides, and then divide both sides by 2 to get x equals 15 over 2. Now, when it comes to equations involving square roots, we need to watch out for extraneous roots. These are solutions that appear to be legitimate, but are not. Here's what I mean. In this equation, we have the square root of x plus 1 is equal to negative 2. Since the square root of a number can never be negative, there can be no solution to this equation. However, notice what happens when we try to solve this equation using the same technique we used for the first 3 examples. When we raise both sides to the power of 2, we get x plus 1 is equal to 4, which means that x must equal 3. So even though we already concluded that the equation cannot have a solution, our technique yielded something that looks like a solution. Since x equals 3 cannot be the solution to this equation, we say that this is an extraneous root. Extraneous roots can arise when we square numbers, as we did in this step here. When we squared negative 2, it turned into positive 4, and this caused our problems. So when we are dealing with equations with square roots, we must be sure to watch out for extraneous roots. Now, extraneous roots can also arise from a slight problem with the property we looked at earlier. Can you see what the problem is here? The problem is that this property does not work for negative values of k. Sure, it works for positive values, such as 9, but it doesn't work for negative values, such as negative 9. So we need to modify our rule such that we restrict the values inside the square root to be greater than or equal to 0. The important point here really is that equations involving square roots can sometimes have extraneous roots, so we need to watch out for them. Here's how we do this. For this equation, we'll first raise both sides to the power of 2 to get 5 minus x is equal to 2x minus 13. To solve this new equation, we'll first add x to both sides, then we'll add 13 to both sides, and finally we'll divide both sides by 3 to get x equals 6. At this point, we must check for extraneous roots. So we'll take the original equation here and plug 6 in for x. When we simplify both sides, we get the square root of negative 1 equals the square root of negative 1. Since the square root of negative 1 has no defined value, we cannot say that the left-hand side equals the right-hand side here. As such, x equals 6 is an extraneous root, which means there is no solution to this equation. Let's try another question. As usual, we will raise both sides to the power of 2. When we do this, we get x plus 14 on the left-hand side, and on the right-hand side, we have x plus 2 squared, which is equal to x plus 2 times x plus 2. When we expand the right-hand side using the FOIL method, we get x squared plus 4x plus 4, and we now have an equation that we can solve for x. Since we seem to have a quadratic equation here, we'll set the equation equal to 0 by first subtracting x from both sides, and then subtracting 14 from both sides. Now that the equation is set equal to 0, we will factor the right-hand side to get the following. Now if x plus 5 times x minus 2 equals 0, then either x plus 5 equals 0 or x minus 2 equals 0. If x plus 5 equals 0, then x must equal negative 5. And if x minus 2 equals 0, then x must equal 2. Now that we have two possible solutions, we must check for extraneous roots. So first we'll test x equals negative 5. We'll take the original equation and plug negative 5 in for x. When we simplify this, we get the square root of 9 equals negative 3. Since the square root of 9 does not equal negative 3, we know that x equals negative 5 is an extraneous root. Next, we'll test the solution x equals 2. Here, when we take the original equation and plug 2 in for x, we get root 16 is equal to 4. Since this solution does check out okay, we can see that this equation has only one root. The solution is x equals 2. So as you can see, we can solve equations involving square roots by first squaring both sides to eliminate the square root. Then solve the resulting equation, and finally be sure to check for extraneous roots by plugging any solutions into the original equation. Now before we conclude this lesson, let's examine one last equation. This one involves a cube root. Now the technique is pretty much the same here. To eliminate the cube root, we must first raise each side to the power of 3. So for fourth roots, we will raise both sides to the power of 4, for fifth roots the power of 5, and so on. Now the cube root of 3x plus 11 all to the power of 3 is equal to 3x plus 11, and 2 to the power of 3 equals 8. From here we can solve for x by subtracting 11 from both sides, and then dividing both sides by 3 to get x equals negative 1. Now when it comes to cube roots, we do not need to check for extraneous roots, because it is okay to have a cube root of a negative number, and those roots are also negative numbers. In the powers and roots module, we learned that if the root is even, as in square roots, fourth roots, and so on, the part inside the root must be positive. However, if the root is odd, as in cube roots, fifth roots, and so on, we can find the roots of positive values and negative values. Okay, let's summarize. In this lesson, we learned how to solve equations involving square roots. We also learned how to solve equations involving nth roots by way of our example with the cube root. To solve an equation involving an nth root, first raise both sides to the power of n. Then solve for the variable. And finally, if n is even, be sure to check for extraneous roots.